Hello, calculus fans! Now up to this point, we've only seen limits that don't exist. So we need to show some examples of limits that do exist and some techniques for proving that those limits exist. So all the techniques that we've talked about before, approaching along lines or various curves, those can never prove that a limit exists. That technique is only useful for proving that a limit doesn't exist. Now, it's the first thing you should try when you run into a limit, but you're never going to be able to prove that a limit does exist using those methods. Now, in one variable calculus, we used limit laws to help us compute various limits. For example, we had rules like this. Limit as x approaches a of x is equal to a. The limit as x approaches a of c is equal to c. So here a and c are constants. Now we can extend these to limits of functions of two variables. The limit of x is equal to a, the limit of y is equal to b, and the limit of c is equal to c. In all of these, we're taking xy to approach ab. We can also use the squeeze theorem, which was another tool that we used in Calculus 1. So, as an example, let's compute the limit as xy approaches 0, 0 of 5xy squared over x squared plus y squared, if it exists. Now, as you'll see, this is actually going to be an example of a limit that does exist. Now we could try to compute the limit along curves that pass through the origin, as we did before. If we were to try this, every limit would turn out to be 0. This is something that you might want to try to do now. And by doing so, it'll seem like the limit is 0, but that doesn't prove it. So let's create this function, f of xy equals 5xy squared over x squared plus y squared. Let's look at the distance from f of xy and 0. That's because 0 is what we think the limit is going to be. So 5xy squared over x squared plus y squared minus 0 looks like this. And we can kind of simplify this by putting the absolute value on only the portion that absolutely needs it. That's the x. So for instance, the denominator is never negative, and the y squared portion is never negative, so we don't need absolute values on those. Now notice that y squared is smaller than x squared plus y squared, and that's because x squared is bigger than or equal to 0. So, a part of this, namely y squared over x squared plus y squared, is smaller than 1. So now, we could say that 0 is less than 5y squared absolute value of x over x squared plus y squared, and that's all smaller than 5 times the absolute value of x. We're now in a position where we can use the squeeze theorem. We know that the limit of 0 is just 0, and we also know that the limit of 5 times the absolute value of x is 0. So the thing that we're interested in is squeezed in between. And since these two limits ended up being the same, we got 0 here, we got 0 here, that means the squeeze theorem can tell us that the limit of the expression that we're interested in also has a limit of 0. So we're not approaching along paths, we're squeezing in between to get to the limit. Okay, that's all for now.